Hello and welcome back to Algebra, the video series where we talk about groups, rings and fields. And in today's part 17, we will still talk about group theory, namely about the order of a given group. Moreover, we will also define what the order of a group element is. However, as always, before we go into the definition, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And moreover, you should know as a supporter you can access a lot of additional material with the link in the description. There on my website you find books, quizzes and PDF versions for the videos. Then, without further ado, I would say let's immediately get into group theory again. There you should know that a group is just a collection of elements, a set with a binary operation. And then both things together have to satisfy three rules, namely we have the associativity, the identity element E, and all the inverses. Okay, so this is a group, and now inside such a group we can also find subgroups. So for example, any element A in the group generates a whole subgroup. And the notation for such a generated subgroup we also already know, we use pointed brackets. So this notation where A is inside the pointed brackets means that this is the smallest subgroup that still contains A. And since we only need one element to generate the whole subgroup, we call it cyclic. And in fact, in the last videos we have already discussed a lot about cyclic groups. Hence now we can use that knowledge all the time, for example, to define the order of an element in a group. For that, let's first recall what we mean by the order of a group G. Indeed, this one we have already used, and it's simply given by the number of elements in the group G. Hence, if G is finite, it's just the cardinality of the set G. In fact, this is the common usage, and in the case that we are infinite, we just use the symbol infinity. Hence, we might still be able to calculate symbolically in this case. And that's it. This is the whole definition for the order of a group. And now we can easily extend this definition and talk about the order of an element A. So the next definition works for any element we can choose from our group G. So maybe as before, let's simply call it A from G. And indeed, the following definition is quite simple because we can just reuse our generated subgroup. Hence we just look at the order of our cyclic subgroup generated by A. So just count the elements that A can generate. So this is not a complicated definition, and I think we can immediately look at an example. And there let's look at the integers modulo 8. So this is a very concrete finite abelian group where we can list all the elements. Namely, we just have the equivalence classes and we start with 0 and we end with 7. In other words, the number of elements should be given by 8. So this is quite easy, the order of the group is given by 8. However, now the next harder question for you would be, what is the order of the element 1? And please note, here we have an additive group, so 0 is our identity element. Therefore you have to answer the question, how many elements are generated by 1? And there it's not hard to see that actually 1 generates all the elements, so we also get out 8 for the order of this element. And then immediately the next question for you is, what is the order of the 2 element? So there you can check what is the subgroup that 2 generates. So you could say we are only allowed to add 2, which means we can get to 4, to 6 and then to 8. Obviously you know that 8 lies in the same equivalence class as 0 and this closes our circle here. So we get 4 elements out, which means the order of the 2 element is equal to 4. And maybe let's look at a final example. Let's take the 4 element. There we don't have to do much because we can immediately see that we can only generate 0 and 4 with it. Therefore what we get out here is equal to 2. This is a really nice example because it shows us that the orders we can get out here are divisors from our group order. So it's easy to see 8 is divisible by 8, by 4 and by 2. And in fact, in the next videos we will talk about this as a general principle. But before we do that, I first want to show you an alternative definition for the order of a group element. So we put this as a proposition, and we can only use it if the order of the element is finite. There, the order is a natural number, and it can be described by a minimum. We can just say it's the smallest possible natural number m, such that a to the power m is equal to the identity element. Indeed, if we have one such m, then we have infinitely many with this property, and that's why we have to go to the minimum. So please note, here we used the multiplicative writing system, and you already know in an additive group this would just mean that we have to add up a m times. And indeed, you immediately see here in the example that we have 1, 2, 3, 4, and we have 4 as the order for a. Therefore, we can also use this order m to describe the whole generated group. Namely, we can just say this one is given by a to the power 1, then comes a to the power 2, and so on. And then the last number in the list is a to the power m, which is our identity element. In other words, these are the m distinct elements in our subgroup. So this makes everything quite simple. Actually, everything works in general like we have demonstrated it in this example. And moreover, I would say more or less, this already gives us the ideas for the proof as well. First, let's use what we already know, how to generate such a subgroup. Here, this one is the smallest possible subgroup that contains A, and it can be written by putting all the combinations together. Which simply means that we have to go through all positive powers and all negative powers. So indeed, this is what we already know. This is how a cyclic subgroup looks like. And now, since we assume that we have a finite subgroup, we know that at some point there will be an overlap of two elements. So let's call the two powers with the same output, which we can definitely find, L and J. So a to the power L is the same as a to the power J, and they are not the same integers. So we can just set that L is the greater one, so L is greater than J. And then in the next step, we can just bring a to the power J to the left hand side. So in short, we can just write a to the power L minus J. And this one is now equal to our identity element E. So in other words, we can definitely find a natural number n that brings us to the identity element. So this is already a nice result, because it tells us that this set we consider here is definitely not the empty set. In other words, the minimum in the natural numbers definitely exists. And in order to keep it simple, let's define this number to be m. And by using this m, we can look at the following subset, which we call U. Of course, you already know this subset because we just start with the power 1 and stop at the power m. And it's definitely a subset in our finite group here. Therefore, the next question would be, is this also a subgroup? The first observation we can make is that all the elements here are distinct, so we definitely have m elements in the subset. Otherwise, we would find a smaller power such that a to this power is equal to the neutral element. And this cannot be because m should already be our minimum. Okay, and now I would say, let's take some arbitrary elements b and c from our set U, and let's put them together with our group operation. Then we can just combine the two powers, and we definitely lie in U again. Simply because if the power gets too large, we can just use that a to the power m is equal to our identity element. So the nice result here is that U is multiplicatively closed, which means we cannot leave the set U by our group operation. And since we have a finite surrounding group, we already know that this property is enough for being a subgroup. However, now the thing is that U also contains A as our generated group here. Which means they have to be the same because the generated group is already the smallest possible subgroup that contains A. And this closes the proof. Now we have a shorter formula for this cyclic subgroup. So the key point is that the order of the element determines everything, and it can be calculated by this formula. And as we have already seen before, there is a relation between the order of the element and the order of the surrounding group. And there I can already tell you that we have a famous theorem called Lagrange's theorem that tells us something about that. However, this is definitely something for the next videos, so I really hope I meet you there again. Have a nice day and bye bye.